Okay, hello everyone again. It's my pleasure today to introduce our speaker, Dr. Fred Roosta-Khorasani. Sorry if I'm
That's okay.
missing pronunciation. He is a data science faculty member in the School of Mathematics and Physics at UQ, University of Queensland. And he is also a senior research scientist at the International Computer Science Institute in Berkeley, California. In 2018, he was awarded a DECRA grant by ARC for his research on second-order optimization for machine learning. Prior to joining UQ, he was a postdoc in the Department of Statistics and Department of Computer Science at the University of California in Berkeley. He obtained his PhD from UBC, the University of British Columbia, Canada in 2015. He currently research into machine learning, numerical optimization, randomized algorithm, computational statistics, and scientific computing. Today, he is going to talk about a Newton type algorithm with complexity guarantee for non-convex problems. Fred, it's your stage now.
Thanks a lot, man. Just a quick question. How many minutes do I have?
I think it's around 50 minutes.
Yeah. Okay, sounds good. Maybe a bit even too much. So thanks a lot for the opportunity. I'll be talking about a little bit about the stuff that we've been doing over the last few years. So it's sort of a series of works that have spanned maybe the last 3 years or so, or 4. So part of it was done when I was in the US, and also a lot of it has been done here, mainly led by my PhD student, Yang Liu, who's graduating right now. And in the US, when I was there, we also Michael Mahoney and Peng Zhu also contributed a lot to this line of work. Now, the idea is, so the main problem is just simple, unconstrained optimization of a smooth enough function. And in our case, because we're really interested in second order algorithms, so we at least require twice differentiability. But sort of the convexity and non-convexity is not really a condition that we focus on, essentially. It could be anything. The goal is to be able to optimize an arbitrarily given smooth function. And as I mentioned, we're kind of interested in second order methods. And if you look at the general framework of second order algorithms, you essentially see them categorized, broadly speaking and very loosely speaking, under 2 sort of categories of methods. Ones that are line search based, where you computed a search direction that mainly comes from a solution of a linear system involving the Hessian and the gradient of the function. Then you choose the appropriate step size and you take a step along that direction. The alternative is a trust region algorithm or trust region framework, where at every iteration you compute the direction and its magnitude all at the same time. So it's sort of like does both 2 steps of line search, you do them all at once. And you sort of update your iterates and move on from there. And so now the question, mainly the focus of my talk, is about how we go about performing these sub problems, because you can abstract away these steps or black box them and say, suppose I have a solution to these, and let me see what the overall algorithm's complexity is or what it's going to do. What I'm going to be focusing on is sort of opening up that black box and look inside and see what you can do and what have been done over the, like mainly in the literature. And if you actually open the black box of the sub-problem solvers, how you go about solving these linear systems, or how you go about solving these quadratic subproblems of truss region, the name that shows up almost 99.99% of the time is a conjugate gradient method. And I'm sure you all have heard conjugate gradient algorithm, CG for short, very classical algorithm, very successful, being used all over the place, in particular, very mainly heavily within optimization algorithms as a way to solve the subproblems. Now, my goal of this talk, or this line of research actually, is to sort of promote the alternative, which goes by the name of minimum residual algorithm, or MINRES, and to sort of say, whenever we come across a subproblem of that kind, we don't have to immediately resort to CG. There are other alternatives that come with much better theoretical and empirical properties. So we try to sort of promote the alternative. But in order to be able to do that, the question that we had from the get-go was, why everyone looks at CG? Why is it that if someone asks you, I have this linear system, how am I going to go solve it? Immediately, the very first response most often is try conjugate gradient. Or if you have a subproblem of a truss region algorithm, you look at textbook, how you're going to go about solving it, the CG style come out. So essentially, at the end of the day, you have this CG as an underlying workhorse for solving the subproblems. So in order to be able to understand that, let's consider the very simple case of solving a linear system as part of, for example, a line search-based algorithm. Now, when the problem is strongly convex, so the function is strongly convex, then your Hessian is going to be a positive definite matrix. Now, if you had asked me this question, I have a linear system arising as part of this line search framework involving a positive definite matrix, what solver should I use? I would have told you exactly CG, no question asked, because when you open up the numerical linear algebra textbook, the first chapter is just background matrices norms, second chapter is linear system, and almost invariably in all of them, CG shows up there when the matrix is positive definite, because it has all these nice properties, it's optimal in terms of its convergence rates and so on, and it's easy to implement, only 4 lines of code, etc., etc. So I would have answered you like that, straight out the textbook answer, maybe if you had asked me this about a few years, like 4 years ago, 3 years ago. But it turned out that the reason perhaps is a lot more subtle than that. And that boils down to the subproblems of CG. So if you open up what CG does, you'll see that at every iteration of CG, my goal is to try to approximate this solution of a linear system. At every iteration, I'll go about forming an approximation to a linear system by solving a quadratic objective, minimizing a quadratic objective subject to a subspace. And that subspace is sort of well known and often referred to as Krylov subspace, which is essentially a subspace spanned by the gradient and powers of matrix multiplied by that gradient. So these vectors, as you iterate, you add more powers of H multiplying G into this subspace, and you take the linear combination of these, and you end up getting a subspace known as a Krylov subspace. Now, why is that important? Is because since K is a subspace, obviously it involves the zero matrix. And as a result, the objective value of this subproblem is always going to have to be a negative number or a non-positive number. And as a result of this simple logic, when H is positive definite, we'll see that the inner product between P and G is always going to be strictly negative, which is a property we want if we are aiming to get descent in our line search algorithm. So it turns out that the main reason perhaps for CG being so popular within line search algorithms, especially when we're dealing with a strongly convex setting is because no matter how many iterations of CG I perform, whether it's one iteration or whether I wait until the end, every single iterative CG is guaranteed to give me a descent direction. Well, but not everything is convex. So most important problems these days, in particular in machine learning, they're actually far from being convex. So what happens when we're dealing with more general problems when the Hessian is no longer positive definite? So in that case, I'm sure you all agree that if, for example, the Hessian is indefinite, then the subproblems of CG could actually be unbounded. So CG breaks down easily because of it. Or even if it's, say, we are talking about a weakly convex function, which is not strongly convex, but happens to have a null space, and part of the gradient lies in that null space, then again, the subproblems of CG can become unbounded. So what happens in that scenario? What can we do to sort of, if you're not able to use CG, what can we do to at least maintain the simplicity of the original linear system, right? We don't want to resort to, because we're non-convex, we don't want to resort to something crazy or some new framework. We want to maintain everything as simple as possible. We started with linear system to compute the direct descent direction. Now we are facing a non-convex problem. Can we still have an easy to solve subproblem that we can work with? Now, as I mentioned, chapter 2 is in any numerical linear algebra textbook is linear system. If you go to chapter 3, you'll see that most likely it's going to be a least squares. However, the least squares that you see in a lot of these books essentially amounts to a lot of times to matrices involving matrices that are tall and skinny or short and fat. Hardly ever you come across a least squares involving a square symmetric matrix. Well, in our case, the least squares amounts to sort of minimizing the residual of the would-be linear system, and the underlying matrix here is obviously symmetric because it's the Hessian of a function. But because we are non-convex, it could be indefinite, it could be singular, and most likely in a lot of cases, it's also ill-conditioned. So how can we solve this linear system? This linear least squares problem? Well, when you're talking about a symmetric matrix in linear algebra, most often the type of algorithms that come out, they are some kind of a MINRES type algorithms. In this case also is the same, no exception, that MINRES type solvers are used to solve these least squares problems, okay? Now, this class of algorithms, what we call Newton MR as opposed to Newton CG, is the class of algorithms that we are slowly but surely sort of expanding on and generating various instances of them for various settings that are Newton type algorithms where we replace CG as the classical subproblem solver, we replace them with MINRES. And this is not a sort of a straight out the box replacement. It actually implies a lot of different theoretical as well as empirical it has a lot of theoretical and empirical consequences that I will go through some of them as part of today's talk. So the same way that I looked at subproblems of CG and realized that CG's iterations always guarantee descent in the objective value, let us also look at the subproblems of MINRES and see what every iteration of MINRES will give us. Well, I was asked earlier on, what is sort of, how do you go about doing MINRES? I'm just going to give you a high level of how we do MINRES right now until I get a bit more into the details of it later. But at a high level, subproblems of MINRES amount to solving a sort of a least squares problem subject to the same Krylov subspace that we saw before in the case of CG. So this Krylov subspace stays the same. The difference now is the objective. Over there was a quadratic. Here is also a quadratic, but involving h squared as opposed to just h. Now, obviously, there is always a solution to this problem, unlike the quadratic problem of the CG, where if H was indefinite, could have been unbounded and so on. There's always a solution to this problem. In fact, sometimes infinitely many so. But importantly, let's look at every iteration of MINRES. Again, with the same line of argument, we see that because this subspace that we are, because the constraint set we are working on is a subspace, again, the zero vector is going to be on it. So this objective function always has to be less than or equal to half of the norm of the gradient squared. So you sort of realize that every iteration of MINRES has to be, by definition, forming a sort of an obtuse angle or an angle larger than 90 degrees with Hessian times the gradient. Now, if you remember, for the CG, the inner product was between the search direction and the gradient was negative. So we got a descent in the objective value. Here we're getting a descent, but it's not descent in the objective value anymore. It's guaranteed to give us descent. Instead of the objective value, it gives us descent in the norm of the gradient. So by switching, just by switching the solver, suppose even we're dealing with the case of the convex problem, the strongly convex problem. So everything is the same. Just by switching from CG to MINRES, you guarantee one giving you descent in the objective value, the other one giving you descent in the norm of the gradient squared. Well, in the case of a convex problem, this might not be a really interesting scenario. The whole premise of my talk today was that what if you want to push beyond convexity and you sort of dip our toe into the non-convex setting. So what does that imply? Like, what functions am I going to be working with for which directions from MINRES actually good directions? So what functions, for what functions the reduction of the norm of the gradient is actually a good thing to do? Well, it turns out that that sort of is equivalent to me asking for what functions the minimization of the original function and the minimization of its the norm of its gradient actually coincide, or they're going to give us the same solutions or set of solutions at the end of the day. And it turns out that there is a class of functions that sits nicely in between the convex and non-convex settings. And if you happen to be in a sort of a workshop last week from the University of the ANU, one of the talks, I sort of touched briefly upon this concept of invexity, which is a class of functions that contain a lot of convex, essentially all of convex functions in there, but also include a lot of non-convex functions. However, the main defining properties of these class of function is that the gradient being zero is an if and only if condition for the global optimality. So you sort of extend the necessary and the sufficiency or necessity of the first order KKT conditions to when they're also sufficient, and they become necessary and sufficient. And in that case, you end up getting a large class of problems called invex, which sit nicely between convex and non-convex. So the directions of MINRES, completely naively, without any bells and whistles, without any other additional steps, if you just compute every iteration of MINRES, they give you a descent, but they give you descent in the norm of the gradient. So if you're talking about an invex function, which include convex functions, you can rely on this direction to essentially make progress. And mental image that you can keep in mind in terms of where invex functions sit across the whole spectrum of functions is sort of like that, which they involve all the convex functions, but also include some extra non-convex settings as well. So the algorithm, the original, the very first Newton-Marr algorithm that we looked at a few years ago is very naive implementation, which is essentially running MINRES. Instead of looking at the linear system, let's look at the linear least squares problem, apply MINRES to it, get a direction that we get at every iteration, chug it into an Armico type line search, but it's a line search in terms of norm of the gradient instead of the objective function, and take a step size and so on and so forth and move along until the gradient is small enough. And you can also simply it's not really difficult at all. Get some convergence results, obviously a linear rate in terms of the norm of the gradient, and under certain conditions, for example, if you're an invex, but in addition, you have this PL condition, which is used a lot within the machine learning community, you can also end up getting sort of a linear, R linear, if you will, convergence rate in terms of the function value as part of this change from MINRES CG to MINRES. But interestingly, you can also get some kind of a error recursion. So let's for now ignore this last term. Let's look at only the first term. And you see that this is reminiscent of the quadratic rate of convergence of CG, which, Newton algorithm, which we always say classical Newton algorithm has the sort of a quadratic rate of convergence locally. That comes about if you assume that the solution that you're in the neighborhood of, it's actually an isolated solution. So it's sort of a strict kind of a local minimum. As part of departing from CG and going to MINRES, you're now allowed to say stuff about convergence to the set of optimal solution, which is what you want if you're talking about invex problems or non-convex problems. So it turns out that going just from CG to MINRES allows you to talk about a linear quadratic type convergence result, but not requiring the isolated local minimum anymore. You can actually talk about convergence or sort of a convergence linear or quadratic to a set of global optimum.
Sorry, just a quick question.
Sure.
GK and the XK, I mean, the GK, are they now the iterates of the MINRES, or what?
These ones?
Yep.
No, this is the gradient of the function. So
of the iterates.
The gradient of the function f. So we initially try to solve minimum of f. As part of the properties of MINRES, this allows us, instead of to minimize f, we can instead minimize the norm of the gradient because they give descent in the norm of the gradient. So g is the gradient of f. Apologies, I should have mentioned this earlier clearly. So g is the gradient of f, and h is the Hessian of the function f. And sort of at every iteration, you ensure descent in the norm of the gradient. And so you can get linear convergence rate in terms of norm of the gradient. You can also get linear convergence in terms of the original function value, if in addition you make some extra assumptions.
Yeah, so I think the point I don't understand is, do you carry out the MINRES to the end? Or?
No, so the thing is that, as I mentioned here, every iteration of MINRES, so the first iteration of MINRES amounts to the Krylov subspace of degree 1, which is just involves one vector in it. Then the second iteration of MINRES is essentially the same subproblem. The difference, or similar subproblem, the difference is that now the dimension of the Krylov subspace now becomes 2. So it's got 2 vectors in it, and so on and so forth. So every iteration of MINRES amounts to solving this subproblem over progressively larger and larger subspaces. So you can terminate after 1 iteration, you can terminate after 2, you can terminate all the way to the end when you actually converge.
Yeah, and that's my question. Which of these possibilities do we see on the last slide you have shown?
This one?
Yeah, so
here it says P is approximately H dagger G. H dagger is the pseudo inverse of the Hessian times G, which this would be the exact solution of our least squares problem. Now here there is an approximation, meaning that you don't need to solve the least squares problem all the way to the end. You can run MINRES and terminate after a fixed number of iterations. There is an actual relative residual condition we have in the paper that says monitor the residual until it gets to a small enough tolerance, then you can pick that to guarantee, for example, linear convergence and so on and so forth.
Okay, then I understand. So it doesn't really matter as long as you don't mess up too much.
Absolutely.
The properties of the MINRES give you what you show on the next slide.
Absolutely.
Okay, thank you very much.
In fact, in practice, you can literally run it for 5 iterations and then chug it into the line search and you're good to go. Yeah, so you never really want to form this exact solution because that's very costly in large scale settings. So another thing that comes up, sort of a natural extension that we had to look into, was that the bottleneck in second order algorithms essentially amounts to working with the Hessian. Hessian is sort of the main problem of main reason why a lot of people resort to first order algorithms and don't look at second order algorithms, because they think that working with the Hessian, rightfully so, is actually quite expensive. So the natural thing for us to do is to be able to sort of make algorithm more efficient by replacing the true Hessian with some form of approximation. A natural way of quantifying this approximation, for example, is just looking at the spectral norm of the approximate Hessian H tilde to the true Hessian being below certain tolerance epsilon. And we can actually legitimately in practice form these H tildes very effectively by leveraging concentration inequalities and so on, in particular in the context of finite sum optimization, where you have your objective function is actually a sum of individual functions. And each one of these functions, for example, in machine learning could amount to a given example in your training data, or if you're doing scientific computing, it could be one measurement that you have in your data set. So when you're talking about a big data regime where the N is large, meaning your data set or training set is very, very large, then computing the Hessian of this amounts to computing the Hessian of the individual matrices n times. So it could be very, very expensive to do. A thing that we have been doing quite a bit successfully in the machine learning community and in optimization over the last few years is by replacing the true Hessian, which is the average of the exact Hessians, with the empirical average of it by forming some kind of a random subsampling. And it turns out if the random sample size is large enough within the tolerance of, let's say, epsilon and some probability tolerance delta, then you can guarantee that the subsampled Hessian is satisfying your desired tolerance epsilon with high probability, let's say 1 minus delta. So we can actually form approximations to the true Hessian to an arbitrary accuracy in a lot of machine learning problems, as long as we're willing to subsample large enough. But now obviously the algorithm stays the same as before. The only difference is that now I'm replacing the true Hessian with its approximation. So in order to introduce efficiency, I replace the true Hessian with its approximation, but everything else stays the same. So now the question is, what are the consequences of this replacement, this approximation? Are we still getting same sort of convergence guarantees? Are we giving up something in return, and so on and so forth? So how can we analyze such a thing? Well, a lot of us have looked at this question within the framework of a Newton CG, in particular, the classical, say, Newton algorithm, where you're talking about a strongly convex function and your Hessian, you invert it, multiply it by the gradient, and you take a step and you go along. And we had looked at this question before by replacing the original Hessian with its inexact variant. And we had looked at the consequences of this. Thing that helped us over there to analyze this resulting approximate Newton algorithm was the fact that we had this spectral approximation guarantee on our approximate Hessian. Because when your Hessian is positive definite and you end up having a H tilde that in a spectral norm stays within an epsilon of the true Hessian, as a result of H being positive definite, you actually end up getting a statement that says the approximate Hessian, its eigenvalue is also within an epsilon of the the eigenvalues of the true Hessian. So we have this spectral approximation. But why is that useful? It's because that also carries over when I put an inverse on everything. So now, as a result of approximating my original Hessian, I end up getting a very good approximation on the inverse of the Hessian as well. So now this is essentially all I need to be able to carry forward my analysis. When the case was invertible and when everything was convex. But now we are talking about non-convex problems, and we don't have an inverse anymore. The best we can hope for is a pseudo-inverse. Suppose I'm talking about the exact solve, which we don't do. But let's, for the sake of argument, let's suppose we could solve MINRES all the way to the end, and the solution that we get is a pseudo-inverse. So instead of an inverse, we have pseudo-inverse. And by approximating the Hessian, we replace it with the dagger. Sorry, with the tilde. So do we have a same condition between the true H dagger and the approximate H dagger, the pseudo inverses of the Hessian and its approximation? Do we have that? Because H dagger is close to H, does that also imply H dagger is close to H tilde dagger? Well, it turned out that the pseudo inverse operation is actually a discontinuous operation unless you can guarantee that the rank of your approximate matrix is exactly the same as your true matrix, which is obviously a very strict assumption to make, because most often when you add a little bit of noise to a matrix, the rank will definitely change. Most often, for example, it increases. So we could not hope to get a condition on this on the pseudo inverse. So that we could not do. There are some, if you look at these matrix perturbation theory books and the literature, you see that there are some bounds on the pseudo inverse of the approximation to the Hessian, but it sort of very badly depend on the norm of the approximate Hessian pseudo inverse itself, which implies that sort of a little o implication on the pseudo inverse of H tilde, the norm of it, which we showed in a paper that contains this stuff, that a very simple perturbation of H by adding a Gaussian noise actually contradicts this. So we cannot make such an assumption. In fact, what perhaps more reasonable to assume is that as I add epsilon perturbation to my true H to get my H tilde, the H tilde dagger should sort of grow in the order of 1 over epsilon. Because you can sort of argue that when H is got 0 eigenvalues, when I add epsilon to it, when I take the pseudo inverse, this epsilon becomes 1 over epsilon. So this is more reasonable. So we could not use these bounds straight from the books. So we looked at, we went back and looked at what MINRES was giving us. MINRES was giving us an iteration P that we needed it to be sort of multiplying H times G, which happens to be the gradient of the norm of the gradient square, right? So if I plug in what P is from MINRES, which is H dagger G, I end up seeing that the inner product between these two is going to be the norm of the projection of the gradient onto the subspace spanned by H. So this UU transpose, it signifies here the subspace of the subspace in the range space of the Hessian. So this inner product amounts to the portion of G that lies into the range of H, the norm of that. So we looked at maybe instead of looking at H dagger and H tilde dagger being similar, maybe we should look at the distance between the corresponding subspaces. So the range space of H and range space of H dagger, maybe those are the ones that are going to be close. Well, we were again out of luck. Again, if your perturbation is not rank preserving, this distance is just going to be 1, so we could not use that either. But thing that saved us was that instead of looking at the distance between the subspaces, which implies the norm of this projection matrices has to be within an epsilon for all vectors V as a definition of a spectral norm, this has to hold for all vectors V. We realized that in Newton-Amar type algorithm, we don't want this distance to hold to be smaller than epsilon for all vectors V. We only care for one particular vector, and that's the gradient. And it turns out by only looking at this quantity, we could indeed bound this distance to within an epsilon. This epsilon is the original epsilon from H tilde and H. The difference between the two shows up here in terms of the distance between the subspaces as seen through the lens of the gradient. There is also another quantity here that's constant that doesn't depend on epsilon that I cannot reduce it to 0. And it turned out we thought at first that this quantity might be superfluous and because of our analysis, but it turned out that actually is a real effect. And I'll show you a couple of simulations there. So now, because of that, because of this sort of a bound that we managed to get, we managed to also bound the iterates of MINRES. And once you do that, then you have yourself sort of essentially everything in place, and you can get a similar type result as the case of the exact setting, where you have linear convergence in terms of the norm of the gradient. You also end up getting sort of local linear quadratic convergence and so on. So almost identical type results to the exact scenario. But in terms of the empirical implications of replacing MINRES with CG, especially when it comes to approximating the Hessian, you'll see that the the percentages are the percentage of the subsamples that we have taken. So as percentage gets larger, your approximate Hessian becomes more and more exact. And this is the performance of, for example, a classification algorithm on this data set. And as you can see, the difference between the exact Newton-MR and its approximate variance using approximate Hessian, it's really not much. And so it implies a certain degree of stability when it comes to sort of approximate Hessian. MINRES adds certain degree of stability, so you can really work with really crude approximations of the Hessian, which is good news because that speeds up the algorithm quite a bit. But this cannot be said when you're using CG. As you can see, the gap between different approximations is going to be huge. For example, in 1% sample size, when the approximation is very crude, and also the 5%, the performance is significantly worse than the case where your approximation becomes more and more accurate or when it's exact. So that sort of says CG is a lot more sensitive to the approximation to my Hessian, which is an important distinction between MINRES and CG. We also threw this inexact version of Newton-MR to some real-world problems. This DenseNet 201 is a neural network architecture. We ran it on CFAR10, and we compared it with almost all the first-order algorithms that people look into these days. And as you can see, in terms of the performance, actually ends up being very, very competitive. Now, the question is how you can make these sort of methods make their way into the machine learning community by incorporating into machine learning packages and so on, which is a work in progress. But these results are really promising when it comes to actual training of real world machine learning problems. Let me skip into this and quickly move on to the, so far I talked about invex problems because we just straight out the box MINRES, no fancy thing on top of it. Line search on the norm of the gradient. If your function is invex, good for you, you can use this algorithm. But if your function is non-invex, then this algorithm could be a horrible algorithm because you can actually go to local maximum. There's no mechanism within the algorithm that says reducing the norm of gradient is going to take me also to the local minimum. It could in fact attract you to a local maximum or saddle point if you just throw a Newton-MR bare bone, no fancy thing around it to a problem that's non-invex. And a lot of problems in real life, they're non-invex. So what do we do in that scenario? Let's see what CG does again, because Newton CG also is applied far beyond convex settings. You can, as I mentioned at the beginning of my talk, when you look at trust region framework for non-convex optimization, you still see CG being used there, for example, as part of CG Stahag algorithm. So if you look at the literature of non-convex optimization, and again, you look at how people are solving the subproblems, you end up seeing, again, name of CG thrown around a lot. In the optimization textbooks, you see that. In the papers, classical papers, CG Stahag, and so on and so forth, you see CG showing up almost ubiquitously as part of the linear system solvers or subproblem of its trust region, even though things are non-convex, because they add some bells and whistles around it to make sure that when it breaks down, they can use that information to make further progress. All the way to more recent developments, very recent developments, led mainly by Stephen Wright, who they actually looked really deep inside CG and managed to actually give finer tuned analysis with a lot of nice complexity, also almost optimal complexity for Newton CG applied to non-convex, arbitrary non-convex problems. So again, let's look at why that is. Why is CG so popular even in the non-convex setting? Well, again, it boils down to looking at the subproblems of CG, which is this quadratic subject to this Krylov subspace. Now, why is that useful for truss region? Why is CG style so popular? It's because if you look at the subproblems of truss region, you see that the optimization, the objective is identical to the objective of CG. The difference is that here, the truss region subproblems involving a unit or ball of radius delta as a constraint, CG involves a subspace. So the subproblems are very, very similar. So that's obviously, you might say, in order for me to solve this, let me try to look at what CG does, because essentially trying to optimize the same quantity, even though looking at a different constraint, but there could be things I can leverage from that. Another thing that you see when you look at the literature, why people use CG for truss region, is that the solutions of CG actually are monotonically increasing in norm, which is a good thing because you start at 0 and you monotonically increase until you hit the boundaries of the truss region. And at that point, you call it a good approximation and you make further progress. But perhaps the most important thing that you'll see why CG is used is because it inherently allows you to detect special type of directions, which we call negative curvature directions. And those are the directions that lie in the eigenspectrum of the Hessian corresponding to negative eigenvalues. And it's very easy to sort of come across those directions because of the way CG is written, which involves this quadratic term. So obviously, the moment I know this quadratic term is negative, then I know that direction must be a negative curvature direction. And we all know that when we have a negative curvature direction, I can use that to also get further descent. And as you can see, this sort of a strategy appearing in all the textbooks and all the papers. They monitor this quadratic, and the moment it's negative, they take that as a negative curvature direction, and they use it as within their approach. But again, this was a bit puzzling for us because that's why everyone is using CG all over again, because there are some empirical results out there that compare CG with MINRES. And in fact, this perhaps is one of the most well-known ones, or at least within the community, that's led by Michael Saunders. He's a famous researcher out of Stanford that actually designed MINRES many years ago. And in this paper, he looks at the performance of CG versus MINRES in a positive definite setting. So it says, even when the system is positive definite, because MINRES can be applied to any symmetric matrix, doesn't need to be positive definite, whereas CG needs you to not only be positive symmetric, but also in addition, obviously be positive definite. So the question that they try to address in this book is that let's suppose we try MINRES and CG for a positive definite system. If you look at the residual, which is the quantity that you monitor when you are terminating solutions of linear system, that's essentially the only quantity that you can compute in practice. It's the residual. If you terminate using the residual as a termination criterion, it turns out that MINRES can converge multiple orders of magnitude faster than CG. And there's loads of other examples in this paper that says MINRES almost always beats CG regardless of the problem. So the question for us was, if MINRES is so good, and we also saw its implications when we were looking at the invex problems, can we move past invex problems and still use MINRES and try to replace CG, if at least empirically we have observed that not only MINRES beats CG in linear system solves, but also in the case of optimization, so far for index problems at least, it definitely beats using CG. So how about arbitrary non-convex? So let's again look at the subproblems of minimums. Residual, it's a sort of a least squares type problem subject to this Krylov subspace. But unfortunately, the problem, if you look at this problem, subproblems of MINRES naively, you'll see that the Hessian here appears with a square on top. So if there is a negative curvature within H, MINRES on its surface apparently should kill it at any moment. So this is actually a bad quantity to look at. So there's no way we can hope for minimum residual or MINRES to give us any negative curvature direction, because the quadratic involves h squared as opposed to h. So we can never hope to get a negative curvature direction. So this was a question that we recently sort of tried to look at. Let's open up MINRES, throw its guts out, knock off the wheels, and figure out whether there is a quantity within MINRES for which we can extract negative curvature when it arises. So the questions we set out to answer was that, first of all, does MINRES come with inherent ability to detect negative curvature, essentially to detect the direction that lies in the negative spectrum of H without adding any additional work? So we don't want to form any new matrix vector products, so we don't want to, at every iteration, we have a vector and form a quadratic. That involves an additional vector, matrix vector product. Every iteration of MINRES amounts to one matrix vector product, the same as CG, which involves one matrix vector product. So without adding any additional computation, can we detect negative curvature? One, and if we couldn't detect negative curvature at the end of all of our iterations, can we certify that the matrix is positive semi-definite? So does it come with a certificate of positive semi-definiteness? And finally, what are the monotonicity properties of MINRES that we can use, for example, within trust region type algorithms? I'm going to switch notation on you very quickly, because this is sort of taken from a paper that we took it out of optimization and looked at it only from the numerical linear algebra perspective. And over there, the matrices are generally A, and the right-hand side vectors are B. So A is my Hessian from now on, and B is my gradient. So A is matrix, B is the vector. Again, the subproblems of MINRES, same as before. It turned out that the quantity of interest to look in our approach is this sort of a Rayleigh quotient, which involves the matrix and the residual of the MINRES iteration in the previous iteration. It turned out that we can compute this. This quantity doesn't appear naturally within MINRES. So MINRES doesn't compute this quantity automatically, but it turns out it gives us two factors, one in the current iteration, one scalar from the previous iteration, that if you multiply these two scalars together, we can actually exactly compute this quantity of interest. And this is indeed a quantity of interest, because I'm running out of time, so let me just move ahead. It's because as part of MINRES, you can show that the sort of the projection of this quantity actually amounts to a quadratic term involving a tridiagonal matrix that comes out as a result of the Lanczos process. And obviously, when the tridiagonal matrix that shows up as part of MINRES is positive definite, then these quantities of interest are always going to be positive. And the question is now whether the converse holds. And it turns out that indeed is true. So if we monitor these quantities within MINRES without having to compute these, right? There's two scalars that I can multiply together and they give me exactly this. So if I monitor them and I realize that up to iteration T, they stay positive, then what I know is that this tridiagonal matrix that shows up as part of MINRES iterations that's related to my original matrix is positive definite. And in fact, I can say that if I iterate long enough and now all these quantities are positive, then the original matrix has to be positive semi-definite. So indeed, it comes with the positive semi-definite certificate. There is also some monotonicity properties that's useful as part of the trust region framework. But the important here is this one right here that says if A is not positive semi-definite, meaning that it has a negative eigenvalue, at some point within my iterations, this quadratic form has to be non-positive. So that means that if at every iteration of MINRES, I monitor that quantity, then at some point I am bound to find if there is a negative curvature, I'm bound to find it, and the direction is actually nothing but the residual of MINRES in the previous iterations. And now we can sort of, equipped with this direction, now we can sort of analyze plug it back into our algorithm and analyze optimality conditions, complexity guarantees for the Newton MR within non-convex settings by analyzing, for example, first order complexity when the gradient is small enough, or second order complexity where the gradient is small enough or the Hessian is approximately positive semi-definite. Again, I'm just going to skip a couple of things. We use an approach by Steve Wright and his colleagues that's very brilliant. Actually, they perturb the Hessian a little bit. I'm not going to be able to get into that. I'm just going to show you the algorithm. It's very simple. We'll look at the gradient. If it's small enough, instead of the gradient, I draw a random vector from a unit ball. If the gradient is small enough. If it's large enough, I just use the gradient itself, plug it into this least squares problem with this little approximation, this little perturbation that I mentioned earlier on from that Steve Wright work. We throw MINRES at this. We get an approximate solution. If the gradient was small and MINRES certified that this matrix is positive semi-definite, which essentially implies that the original matrix is approximately to within epsilon positive semi-definite, I'll terminate. Otherwise, if I'm not guaranteeing any of those, that means that either the solution I've gotten satisfied certain residual tolerance, or MINRES has given me a negative curvature direction. Either case, I'm happy. I'll just chug it into this line search and I find the alpha. The cool thing about this algorithm is that I can start from step size of 2 versus step size of 1. And that's a direct consequence of using MINRES as opposed to CG. MINRES sort of has this relationship between G and H and the solution of the CG iterations, whereas MINRES doesn't have this 1/2. And that alone allowed us to start the line search for CG, Newton CG, with alpha equal 1, whereas for MINRES starts with alpha equal 2, which is twice as large, allows us to take twice as many steps or larger steps, and that has significant practical performance implications. Operation complexity, to first order guarantee, we get bounds that are known to be optimal. So essentially this algorithm matches the optimal algorithms that use CG by replacing MINRES. So the theory is identical, but the empirical performance is significantly different. So I have only 2 more slides. So if you look at, let me show you some real problems such as autoencoder on some real data sets from machine learning. The purple curve is the Newton CG and the black curve is Newton MR. And the difference is staggeringly large. It's because this difference between the step size of 1 and step size of 2, it massively changes the way algorithms are performing. In terms of time also, it's different. And when we also threw these algorithms on the QTest problem, 250 of them, this is a performance profile. And as you can see, the Newton MR lies significantly on top of Newton CG, pretty much on every front. Using MINRES is an advantage over using CG. So this is the end of my slides. I'm sorry I went over a couple of minutes, but I'm happy to take any questions.
Thank you, Fred, for your very nice talk. Yeah, no problem with the time. Yeah,
okay.
You're right. And now it's the time for discussion. Anyone, if you have question or comment for Fred, please unmute yourself and ask a question, please.
Yeah, I might have a question then. So in all these algorithms, you're presuming you've got access to the Hessian. You're not approximating the Hessian by using a rank 2 BFGS or DFP type thing.
Excellent question. So for now, the case of the invex problems, our approximations depend sort of on the subsampling versions. We didn't look at the quasi-Newton approximations. For the non-convex setting, what we have done so far, we require having the exact Hessian. Although we never formed the Hessian explicitly, we always need a Hessian vector product because MINRES doesn't really care about having the matrix explicitly available. It only requires a procedure that takes in a vector, it spits out a matrix vector product. And we can do that in machine learning very easily by these backpropagation algorithms. So it's easily done. But beyond that, it's a very good question. That's exactly what we are looking at. What are the consequences of, for example, applying SR1 type approximations or even BFGS type approximation and using MINRES? Now, why is that good? It's because one thing we have when we do quasi-Newton, I'm sure you know better than me, is this sort of a Wolfe type conditions we need to guarantee in order to maintain positive definiteness of the quasi-Newton matrix. And so what happens now, and we need that positive definite because we need to get descent. But now MINRES, we know we can get descent using negative curvature that it detects. Also, it doesn't need positive definiteness anymore.
Yeah, that's
so
yeah. Yeah, sorry. That actually comes to sort of another thing I was going to ask you was that you know that with say BFGS and the DFP approximations, one thing's known is that the BFGS is preferred because it stays more positive definite. You know, the F to P kind of go indefinite. You know, and so that's really what's behind a lot of the numerical observations about its use. But of course, that's not really an issue with your MINRES, is it?
That's right.
And also, I mean, people, when it comes to sort of trust region methods, you know, rank one approximations allow negative curvatures to occur.
Absolutely.
And I'm just wondering whether, you know, there's something there that can be utilized.
Absolutely. It's a wonderful observation, 100%. It's in fact the thing that right now we're looking into is sort of exactly that. So you ideally would just want to have backtracking lines, so you don't want to do any kind of nonlinear Wolfe condition because you want to maintain positive definiteness. And what happens when you do line search for BFGS, you lose the positive definiteness. And what happens when that happens, you sort of skip the quasi-Newton update. Whereas if you don't need to worry about positive definiteness, you can keep on updating your quasi-Newton matrix because you don't need to have positive definiteness. And 100% agree with the trust region framework where people use, for example, SR1, this rank 1 updates that, in fact, they're preferred over there because then you end up getting the negative curvature. Again, we're looking at that to sort of look at what MINRES does in that framework.
Yeah, okay, thanks, Fred.
Sure.
Thank you, Andrew. Any other questions?
Yeah, hi, not very deep questions. So one question is, as far as I see, MINRES, every step of MINRES is more expensive than a step of CG because you have to kind of keep track of the subspace you're working with. But is it possible that you need so few steps of this MINRES that this doesn't really matter because this subspace doesn't grow too much?
So let me disagree with the first assertion. So it actually, the cost is almost identical. There is no difference at all because all of these things, when we write it down at a high level. But when you implement them, there are tricks that people do that, you know, it's sort of, you can move things around and so on, that becomes essentially of the same order of magnitude in terms of complexity. Each iteration of MINRES and CG amounts to one matrix vector product. The only difference is that in MINRES, you probably have to store one additional vector compared to CG. So the cost is in terms of storing one additional vector, which perhaps is negligible. And these subspaces for both of them are automatically enlarged, so you don't really maintain any sort of a basis of any kind. Everything is automatically stored. I remember you mentioned about GMRes. GMRes has this issue that as you iterate more and more, you're maintaining larger number of vectors because it's applied to non-symmetric matrix. But because we're talking about a symmetric matrix here, the MINRES is got the exact same three-term recurrence relation that CG has. So essentially, it's the same sort of an algorithm. You need to go through the same sort of a procedure as CG. And let me just say one more thing. You can actually look at CG and MINRES in a beautiful way that you see how connected they are. So we have, when we form this tridiagonal system, this relationship appears for CG as well. So the difference between CG and MINRES can be looked at this way. The CG can be derived by forming the Cholesky decomposition of this tridiagonal system, whereas MINRES can be derived by forming the QR factorization of this. So essentially, both of them amount to the exact same amount of work. It's just the different approaches, psychologically or abstractly speaking. But in terms of cost, one vector additional you need for MINRES that you don't need for CG.
Okay, I didn't know that.
Yeah.
Mm-hmm. And then there was another thing. in the numerical results you show,
Yeah.
it's very characteristic that the that your method has sharp drops and then kind of plateaus. Do you understand where that comes from?
Yeah, so this is a very good question. I think it has to do a lot with the when we hit areas which there's a lot of negative curvature. So I think negative curvature is a good direction, but you perhaps you want, when you take them, they're not maybe as good as any other direction. So if you look, for example, Newton CG up here, unfortunately, constantly is hitting negative curvature. And that's why it's sort of plateauing up there. Whereas here, there are steps in between that we are not hitting negative curvature, is because we are allowed, we are able to work with indefinite matrices, so we can iterate. In CG, the moment you hit negative curvature, you have to terminate. There's no other thing you can do. But in MINRES, you can keep on working because there's nothing breaks down until you know that, okay, there's nothing more coming, so I need to work with my negative curvature. So a lot of these steps that we actually go down are the steps that we found a solution, not a negative curvature, essentially an approximate solution, and those are better in our experience.
Mm-hmm. Okay, thanks.
Sure.
Okay, thanks. Any other question or comment? First, I'm a bit curious about the invex functions.
Yes.
Do you need Invexity for the proof of conversion, or you just need for the fact that every critical point is
yes,
global?
yes, very good. So for the for the non-convex, we don't make any invex assumptions, obviously. But
Okay.
the original time, well, initially when we looked at this and we looked at the invex, it's indeed, as we don't really need invex assumption. It only shows up because we want this relationship to give us something meaningful. Otherwise, it can give us a critical point that we're not interested in. Having said that, so we just use it as sort of as interpreting what could be useful. Having said that, there was a couple of papers follow up on our work that looked at our Newton-Nomura algorithm not as an optimization algorithm, but as a root finding algorithm, because they're actually interested in finding the roots of a neural network, because that sort of tells them something about various generalization performance of different parts of the neural net. So they actually looked at our algorithm versus the classical root finding algorithms, and they saw that this actually does better than the other ones in terms of finding saddle points. So yeah, you're right. We just use it as sort of justifying when it's useful, but technically speaking, we never need for any proof. No.
Okay, thank you. That's
Very good question.
Yeah, interesting. Okay, so if there is no more question or comment, let thank speaker again.
Thank you so much for the opportunity.
And we will have another talk this afternoon.
Fantastic.
Yeah.
And I'll be happy to, if there's any question that you didn't get a chance, shoot me an email or whatever. Zoom is easy these days to set up. I'll be happy to discuss.
Okay,
right.
Thank you.
Thanks a lot, everybody.
Yeah, thanks
you.
so much, Fred.
Absolutely.
Thanks
For the invitation.
Yeah.
Cheers.
Thanks, Fred.